The second special case is when there are an infinite number of solutions. Any value of x that you plug into the equation will make the equation true. Let's look at an example of that. 2x minus 1 minus 4x equals negative 1 minus 2x. First step is to simplify the left-hand side. Negative 2x minus 1 equals negative 1 minus 2x. Next, I move my variable term. So I add 2x to both sides. Again, in this case, there is no other option. To move this guy, I add 2x. To move this guy, I add 2x. Negative 2x minus 1 plus 2x. I just end up with negative 1 on the left-hand side. On the right-hand side, I have negative 1 minus 2x plus 2x. So I end up with the same constant. So when I end up with the same constant on both sides of the equal sign, I have a true statement. Any value of x will make this equation true. So there's two different questions I could be asked. I could be asked, how many solutions are there to this equation? And if you're asked that question, ending up with the same constant on either side of the equal sign, the answer is there are an infinite number of solutions. However, the actual solution is all real numbers. All real numbers, which I like to write as this bold R. It's not an IR, it's a bold R, or a fancy R. So the solution is all real numbers because any value of x that I plug into this equation will make the equation true. Negative 1 always equals negative 1. Please don't be confused and stop at negative 1 equals negative 1. That is not the solution. Similarly, for this equation, don't stop at negative 1 equals 9. That's not the solution, that's just the work. Now, there is a lot of room for finding this answer but not having the proper justification. So in this case, a lot of students will want to stop at, for example, negative 2x equals negative 2x or x equals x. That is not considered sufficient justification. You need to continue to solve until you have a constant equals another constant. And then you can say the solution is all real numbers. If you would have added 1 first, or if you want to continue adding 1 to both sides here and you stop at 0 equals 0, that's okay. So 0 equals 0 or negative 1 equals negative 1. On the previous case, negative 1 equals 9. 0 equals 10 or negative 10 equals 0 would have been okay. But it is not okay to just stop with the variable terms on each side. It's also not okay to just stop at negative 2x minus 1 equals negative 1 minus 2x and realize, hey, this is going to have an infinite number of solutions. The solution is all real numbers. It's great if you can recognize that, but you have to solve until you get to a constant equals another constant. The way you check your work when you have a special solution is you look for this pattern. So the no solution case is when you have the same coefficient in front of your variable but different constants. There can be no solution to this equation. I can't have x, multiply it by the same coefficient m, and then add a in one case and a different number b in another case. Those two things will never be equal. So x times m, same thing still, add a, add something different. Those two things will never be equal. However, in the infinite solution case, same coefficient times m, add a. Doesn't matter what I started with. If I multiply the left-hand side by m and add a, multiply the right-hand side by m and add a, I will always have a true statement. So this is how you will check your answer. You'll look for this pattern, but you cannot just stop here. To justify your answer, you have to get to the case where constant equals constant. If those two constants are the same, all real numbers. If they're different, no solution.